All right, let's get started again here. So, I want to talk more about coordinate change and quadratic forms and how that ties in with this Sylvester's theorem. All right, um, so let's just look at how coordinate change works a little bit. So if beta is a basis for Rn, then this is the basis matrix formed by just taking the vectors in the basis and stringing them out into a matrix, standard notation. Then v with a sub beta is my notation for the coordinate vector of v, which you can get from multiplying by the inverse of the basis matrix times v. One of the reasons orthonormal coordinates are so awesome is that this becomes just a transpose of the basis matrix, and it's pretty easy to calculate. But generally, you got to invert the thing. All right, anyway, that gives us the coordinate vector of v with respect to the basis beta. And as we talked about, the standard matrix of a quadratic form is denoted like this. That means that the formula for the quadratic form can be written q of x is x transpose times the matrix of the quadratic form times x again for all x. So what would happen if we, say, changed coordinates on the quadratic form? All right. So I think I did this before. I'll do it again because I wanted to compare two different quadratic forms. So I take the formula, I sandwich in the identity matrix. If I had some whiteout, I might have killed this and just went straight to here. Sorry. But really that's the basis matrix times the coordinate vector, basis matrix times the coordinate vector. And so by the usual socks, shoes, transpose rule, you get that. And so you look at that and you go, oh, so if I use the coordinate vector with respect to the beta basis, then this is the matrix. All right, so definition, Q sub matrix of Q with respect to the beta basis is given by the transpose of the basis matrix times Q, standard basis times the basis matrix again. Great. So that, naturally the question that comes up then is like, oh, what if I chose a different basis, right? Because the choice of basis beta is by no means unique. What if we chose, say, a gamma basis, right? Because if we had a gamma basis, then we'd have that Q of V is this, which is V transpose the gamma coordinate transpose times the gamma matrix times the gamma coordinate vector again. And so to relate the beta and the gamma coordinate expressions, I think it's good to do this. I just kind of took a pretty lowbrow approach. I just solved them both for the standard matrix of the quadratic form, and when I do that I get this. And then when I solve for that, I get the transpose of the beta matrix times, I've used something a little bit sneaky here, the transpose of the inverse is the inverse of the transpose. You read my sentence, which way up or down you need to go there. And then I multiplied by the beta matrix on both sides, which got me to this. So apparently, what's going on here? Well, that's the relation. So if we want to go from the gamma coordinate expansion for the matrix of the quadratic form to the beta matrix for the quadratic form, we have to multiply by this on the right and that on the left, which is kind of a little bit awkward. But if you introduce some notation, say m is equal to the beta matrix and n is equal to the inverse of the gamma basis matrix, then you can see that what we got here is that the Q sub beta is m transpose n transpose Q gamma and m, but sock shoes says that's nm transpose. And so there you go. That's the kind of transformation we're looking at for a quadratic form. It's a sandwiching between a transpose of a matrix and a matrix again, where the details in terms of the corresponding basis involved are given here. But in summary, the coordinate change for a quadratic form follows this kind of pattern. We take the matrix and we convert it to another matrix which is formed by the transpose of some invertible matrix times a invertible matrix again, same one. This is a pretty big contrast to the way coordinate change works for a linear transformation, right? Maybe you remember, if we have a linear transformation from Rn to Rn, then if you study the matrix with respect to giving the same basis for the domain and the codomain, the rule for coordinate change there is that we have the similarity transformation, right? So if you look at the matrix of a linear transformation with respect to a given basis, then another basis, well, those two matrices are going to be related by a similarity transformation. In other words, the matrix of a transformation transforms by similarity. Well, the matrix of a quadratic form does not transform by similarity. It transforms by this, which is quite different. And so if you're not careful and you use intuition that you've gained for how a linear transformation transforms on the matrix of a quadratic form, it could get you into trouble. All right, well, Sylvester's theorem tells us a little bit about some things we can, the rights and privileges that we're entitled to if we do change coordinates on the quadratic form. And what Sylvester's so-called law of inertia says, this is from Spielmann's section 3.1, it says if we have any symmetric matrix and B is any non-singular matrix, then B transpose AB has the same number of positive, negative, and zero eigenvalues as A. So let's look at his proof for that, and let's see. I'll try to go through it quickly here. So first of all, the proof is in two stages. So first of all, we notice that similar matrices have the same eigenvalues. So let's see. Okay, how's that go? If M is BAB inverse, that means M is similar to A. So if we have a non-zero eigenvector with eigenvalue lambda, AV equals to lambda V, right? But if we then look at M times BV, well, M is BAB inverse times BV, but B inverse and B cancel, which just leaves me A times V, but A times V is lambda V by assumption, and then I can pull the lambda out and I get lambda BV. But then, that just shows you that M times BV equals to lambda times BV, which is to say that BV is an eigenvector with eigenvalue lambda for M. But remember, V was by assumption, eigenvector with eigenvalue lambda for A. So apparently, M and A both have eigenvalue lambda. In other words, A having eigenvalue lambda implies M has eigenvalue lambda. And you can make a very similar argument for the other direction. If M has eigenvalue lambda, it forces A to also have eigenvalue lambda. So you can see that M and A share the same eigenvalues. Similarity implies that the spectrum of the similar matrices is identical. Now, this of course is not surprising if you've studied like Jordan forms and such, but let me not digress. Now, part two. And this is where it gets interesting. All right. So, by the QR decomposition, you can, and this is using that Gram-Schmidt hocus pocus, so to speak, you can find a orthogonal matrix Q and a upper triangular matrix R with positive diagonal entries, such that B is equal to QR. This is the QR decomposition. And then we use a trick. We form a path of matrices. For each T, I give you a matrix R sub T. That's a path. And this is a standard trick. If you plug in T equal to 0, this goes away and it just leaves you 1 minus 0, which is I. So the R sub 0 is I, or in MATLAB, IN. And if we put in T equals to 1, well, we get 1 minus 1, which is 0. That goes away. We're just left with R. So this is like a standard calculus 3 trick to get a path of a line segment between 2 points. But in this case, those 2 points are matrices. Anyway, this gives us a nice continuous path between the identity and R is what's going on there. And then, sneakier still, we define a family of matrices, M sub T. All right, and so this is, I guess, another path, if you like, of matrices. But this time we define it a little bit differently. We use that R sub T times Q transpose times A times Q times RT. And the reason to look at this path is because its endpoints correspond to two things that we have a pretty good handle on. All right, let me explain. So the first thing, T equal to 0. When you plug T equal to 0 in, you get r sub 0 q transpose a q r sub 0. R sub 0 is the identity, which means that this is just q transpose a q. But remember, q is orthonormal, which means it's q inverse aq, which is what? This is a matrix similar to A, which means that m sub 0 has the same spectrum as A, straight up the same spectrum. Now, t equals to 1 gets us R transpose Q transpose AQR, which by Sock's shoes is QR transpose AQR. All right, well, okay, so what? And there's more we can say here. So you can think of this direction sort of being time, right? T progresses from time 0 to time 1 as you kind of go down there. So let's see here. What else can we observe? Like I said, M0 has the same spectrum as A because M0 is similar to A. A is symmetric. So, have I seen your monkey? I have not seen your monkey. I bet it's upstairs. So go looking for it there, okay, buddy? All right. See you, Benjamin. So, I always got to find the monkey. Need the monkeys. All right, let's see here. Somehow I've gotten distracted. Oh, yes. So M sub T transpose is that, and that's that. And then by the socks, shoes rule, which is you put your socks on, then you put your other socks on, then you put your shoe on. To take them off, you first have to take the shoes, and then the outer socks, and then the inner socks. So it's like that. But anyway, I'll shut up. It gives you this, but the transpose of the transpose is just the matrix again, and so lo and behold, we're back to where we started. So at each time between 0 and 1, M sub T is symmetric, all right? So that means at each time from 0 to 1, the eigenvalues of M sub T are real, right? And we can also notice that the rank of M sub T is equal to the rank of A because QR sub T is non-singular. Because R sub T is a positive diagonal matrix, the matrix with positive diagonal entries, and Q is, so that means that R is non-singular and Q is non-singular, so Q times R sub T is also non-singular, and so since QRT is non-singular and that's non-singular, that means that M sub T has the same rank as A, which also means that, okay, we'll get to it. Well, that also means that the nullity of M sub T is equal to the nullity of A. In other words, the number of 0 eigenvalues of A must match the number of 0 eigenvalues for M sub T. Now, furthermore, the eigenvalues of a symmetric matrix are continuous functions of the matrix coefficients, which he claims is something that is more or less proved in lectures 4 and 5. I'm willing to accept it for the moment, but he points out that because of this continuity, it follows that the number of positive and negative eigenvalues for A must match the number of positive and negative values for M sub T, and hence also for B. So we can kind of track from here to here. Q transpose AQ has exactly the same spectrum as A, and as T evolves, it can adjust the eigenvalues, right? But it can't change their sign. And the number of 0 eigenvalues is constant throughout this time evolution. And that's a somewhat complete sketch of Sylvester's theorem. He gives a rather different argument in the next two lectures, which I probably won't go through because I think it takes us too far afield of where I want to go with these talks here. Anyway, that's Sylvester's theorem. All right, so now there's some other results from lecture 3 which I'd like to just go through quickly. If M is a symmetric tridiagonal matrix with 2p positive off-diagonal entries such that one is in the all one vector, that I haven't written it here, I should write it here. This guy is this guy. So if you have 2p positive off diagonals, then it has p negative eigenvalues. On the other hand, similarly, if you had 2p negative off-diagonal entries, then you'd have p positive eigenvalues. So since the theorem we had from back on page 23 applies, we can notice that the condition I less than j pretty much means that j has to be I plus 1 because of the tridiagonal condition. In other words, we can write this expansion for m is equal to the sum I equals 1 to n minus 1 of m sub I comma I plus 1, like that. And so that's just kind of neat. But also by the theorem on 24, our weighted sum of squares formula theorem, we can rewrite this as, minus m I plus 1 else x sub I minus x sub I plus 1 squared, right? And then I got a little bit confused because he does something sneaky here and doesn't quite say what he's... he's really making a change of summation in what he does there. I would say switching I plus 1 equal to j, and when you do that, instead of I starting at 1, you'll have j starting at 2, and going, not instead of n minus 1, it'll go to n, and instead of having I, you have j minus 1, instead of having I plus 1, you have j, and that would give you this difference squared. Again, sorry, I haven't had it white out. And if you introduce this new system of coordinates, delta 1, delta 2, delta 3, delta n, like so, well, then you can add these up and see that if you add like the first two, right, then let's see here, x1, let's say delta 1 plus delta 2. The delta 1, x1's cancel, you just live with x2, right? So x2 would be delta 1 plus delta 2. x3, if we take delta 1 plus delta 2 plus delta 3, these guys cancel, and those guys cancel, and you're just left with x3. So x3 is delta 1 plus delta 2 plus delta 3. And so the story goes. And so if we make that coordinate change, I'm claiming it's a coordinate change, what does it need for it actually? What does a coordinate change have to have? It has to have invertibility of the coordinate change matrix, doesn't it? There's a hint about that homework. Yeah, if we write that out as a matrix, we've got x1 through xn, delta 1 through delta n, x1 is equal to delta 1, delta 2, plus delta 1 is equal to x2, and finally delta 1 plus delta 2 plus delta n is equal to xn. And that's how you change from the x to the delta coordinates like that. Notice that this is an invertible matrix because it has 1s down the diagonal, which means this has eigenvalue 1. Anyway, the determinant of this is 1, so it's invertible, right? L inverse exists. So, by Sylvester's theorem, L transpose ML has the same number of positive, negative, and 0 eigenvalues as M. Okay, so that's... Oh, yeah, all right. Well, okay, sure. And we can also notice that X transpose MX is L delta transpose ML delta, but explicitly this is given by that, which is, delta transpose that delta vector, the delta vector here, and then this is the matrix. And from this you can see that we have eigenvalues 0 and minus m1 comma 2 all the way down to lambda n. Sorry, I got a little small there. And minus 1 comma n with a minus up front. And so of course if the off-diagonal entries, which are these numbers, are positive, then as many of those are non-zero, well, that's as many as you have positive eigenvalues. So, yep. Now, it's important though, so that, I'm trying to say here. So what can you say about the spectrum of M from this? I mean, clearly this matrix, L transpose ML is a diagonal matrix, right? So you can just read, that's this matrix. Then the eigenvalues are explicitly, it's a diagonal matrix, you can read the eigenvalues, right? So how do the eigenvalues of M correspond to this? Well, they don't have to be the same, right? because L transpose doesn't have to be L inverse, right? But we do know by Sylvester's theorem that the eigenvalues of M must follow the same pattern, right? The eigenvalues of M must also have, you know, 0 is one of them, and there are as many positive, well, in this case, there's many negative eigenvalues in M as there is in this L transpose ML matrix. Let's see here. Got a little bit more to say here. Now, so Spielmann uses that result, I believe, to prove this theorem. So this theorem stated at the start of the section, his lecture 3, but then he kind of spends the better part of that lecture developing results to prove it. And this is actually pretty tough, I think, to get through the entire proof of. So I'm actually just going to illustrate it with an example. But I've shown you a lot of what's needed to get through the proof. I'm just not going to quite get there. I hope you can forgive me. So let P be a weighted path graph on n vertices. And then suppose that the graph Laplacian of P is denoted L sub P and it has eigenvalues lambda 1 through lambda n, where Vk is the eigenvector of lambda k. Then, here's the punchline, Vk changes sign k minus 1 times. In other words, that thing we observed for the weight 1 path graph continues to happen for weighted paths. And so that's pretty cool. Here's an example. If we take this 6 path, 6 edge, 6 vertex path, there's 5 edges, and I gave them odd weights, 3, 5, 7, 11, 13. And great. Well, actually, they're prime, but they're also odd. Anyway, I'm being stupid. Here's the graph Laplacian. Just want to show you how that theorem actually plays out for this example. And I put MATLAB to work here. So here's the graph Laplacian for that 6 vertex set. And we use the eigl to get the matrix of eigenvectors. Right? That's that basis matrix I've been talking about, basically. And B, of course, it gives you back a diagonal matrix with the diagonals. I guess we called this big lambda earlier. But as you can see, the 0 eigenvector, constant, right? The second one has 2 minus 1 sign changes, and it's got 1 sign change, right? The third one has 2 sign changes, right? Minus to plus, plus to minus, right? The fourth one has plus 1, 2, 3 sign changes. The fifth one has 1, 2, 3, 4, I can't count. 1, 2, 3, 4 sign changes, and the sixth one has 5 sign changes. And oh, something else to notice here is this is a graph with 6 vertices, right? But notice that the eigenvalues are not bounded by 6, right? Last time we showed that the eigenvalues have to go between 0 and n, but there was an important consideration there. The weights had to all be 1. When you let the weights be larger than 1, there's no bound on the spectrum. Spectrum could be whatever. It could be as big as you want. Well, there's probably some kind of bound, but anyway, this one, even though there's only 6, the eigenvalue here, the top one is 37.68. So be careful as you're applying theory that we're applying it correctly, right? So you got to watch out. Some of the theorems are just for weight 1 graphs. So in summary, here are some of the things that Spielmann gave us in his lecture 2. Some of these we've looked at explicit examples for before. I think all of them actually at this point. You have the complete graph on n vertices kn. You have the star graph Sn. You have the path graph Pn, and you have the ring graph Rn. And the edge sets, complete graph, just everything's connected. The star graph, everything, we use 1 for the star center. Path graph just connects adjacent points, and then the ring graph, it connects adjacent points, and it connects the first to the last. All right, so I think the calculations are actually kind of fun, so I'll walk through them here pretty fast, but let's see here. course, you can always skip past things you're not interested in. So since Kn is connected, we have that the second eigenvalue is positive, hence only lambda 1 is equal to 0. Now suppose you have another eigenvector, all right? The claim here, the lemma 2.41, is that you have just two eigenvalues, really, distinct eigenvalues, 0 and n minus 1. So let's see how that happens. So the 0 is because it's connected. The other one, though, well, let's just suppose we've got another eigenvalue, lambda. LV equal to lambda v. Now we do know that that v has to be perpendicular to v naught because the spectral theorem, among other things, says that the eigenvectors from distinct eigenvalues are perpendicular for a symmetric matrix. And of course the graph of Laplacian is that. And we have the LV naught is equal to 0, but we also know that v naught is the 1, 1, 1 vector. And so that tells us that this vector v we're trying to get our paws on, the sum of the components of it is 0, right? But let's suppose that the jth component is non-zero. One of them has to be because it's an eigenvector, so it's a non-zero vector, right? So at least one component must be non-zero. And so we can solve for that component as the sum of the, the sum of the minus, good grief words. Vj is minus v1, minus v2, minus dot dot dot, minus vn, where this hat means that I'm omitting the jth one, right? Okay, great. Well, if we look at the jth component of LV, that would be the lambda times the jth component of V. But of course we can expand that matrix column multiplication like so, and when you do that, you get that. But explicitly, if you think about the graph Laplacian for the complete graph, we're assuming that the complete graph has all weight 1, right? So the weights are all 1. This is from lecture 2, where the weights are all 1. And so that means that there's, see here, I'm trying to think of how to explain this. So LJV1 is minus V1, LJ2 of V2 is minus V2. Because there's just a minus 1 in that component. There's a minus 1. Like this is minus 1, that is minus 1 when you look at the graph Laplacian for the complete graph. Well, every component, every off-diagonal component in the complete graph with weight 1 is minus 1, right? So it's a no-brainer, minus 1, except for the diagonal one, right? The diagonal one has to be equal to n minus 1 because the sum of the things in any column has to be 0, right? So if there's n minus 1 minus 1's there, then the diagonal one must be n minus 1 so that when you add them together you get 0. And we get that. Now if I collect everything here except for Vj, I've got that up here, so that gives me a Vj, which is why I got to get Vj here. From collecting all these minus terms together, or rather collecting all the negative terms together, which gives me this plus that. Which, of course, can't do in the algebra here, gives me n Vj is equal to lambda Vj, but remember Vj is non-zero, so therefore lambda equals to n. And, oh man, I wanted to get lambda equals to n minus 1. What has happened here? How have I seized? Well, I'm gonna say this is a typo. Let's hope I'm right. All right. So on to the star graph. So if we have a star graph, that means that, well, we're going to get that. First there's this lemma, which I think is worth a moment or two of time, because I think this might be useful to notice in certain places. If we have a graph and we have ij or degree 1 vertices and they're both connected to k, like in my picture, then if you construct the vector with uth component as 1 if u equals to I, minus 1 if u equal to j, and 0 otherwise, then that's an eigenvector for the graph Laplacian with eigenvalue 1. Here's the argument. So we're given I and j have degree 1, which means that ik and kj are in the edge set, since they're connected by k, right? And it follows that the ith column of LG has to be EI minus EK, because there's only a connection between I and, it has degree 1, right? There can only be 2 non-zero entries in the ith column. And likewise, by construction, column J of LG is EJ minus K. But if you look at the VU, well, that's really EI minus EJ with the standard basis. And so if you calculate LG times this V, you get column I of LG minus column J of LG, which gives us EI minus EK minus parentheses EJ minus EK, so the EK's cancel. And you got E minus EJ again, which is what we started with, which means that LGV equals to V, which is to say that eigenvalue 1 we obtain for V, for this kind of, if you have this, if this happens in your graph, right? Anytime you have a graph which has has little things hanging out, just connected at one thing to the graph, right? The graph could go on from here, could have tons of nodes, but if this is hanging out here like that, well, that gives you a eigenvector with eigenvalue 1. Kind of neat. And I also noticed that this could be, I tried to generalize it, like what if the weights aren't 1? Can we do anything there? Like what if we have weight alpha and weight beta? Could I tweak this argument for that? And I tried. My intuition was to try for beta EI minus alpha EJ, but when I did that, I got back to alpha beta EI minus EJ, which just didn't quite match what I started with. So I was like, phooey, it won't quite work. But if I do let alpha equal to beta, then the argument works. In fact, I get that if alpha equals to beta, in other words, if I've got a weight alpha between I and k and between k and j, then the vector v equals alpha times EI minus EJ gives a... well, this is silly. You don't really need the alpha there. You could just use EI minus EJ again. Anyway, the vector EI minus EJ gives you eigenvalue alpha. You could put any number here. It's an eigenvector, right? So you can rescale it however you like. Putting the alpha there is just an artifact of my silly experiment here. But anyway, I'll go on. So the star graph actually has eigenvalue 0, and then 1 repeated n minus 2 times, and then n at the end. So again, since it's connected, we know lambda 1 equal to 0. And without loss of generality, I'll suppose I is less than j. And notice that we can connect 1 to I and 1 to j, so we can apply that lemma. And that will allow us to construct a vector like Vij equal to EI minus EJ, just for the sake of discussion. And we can do that, for a lot of choices, but, if you select 2, 3, 3, 4, 4, 5, 5, 6, n minus 1, n, well, these will be linearly independent vectors, all with eigenvalue 1. So that give me that. And I count n minus 2 of these guys. And then that leaves us with one eigenvalue to go. But notice that, so I think I argued through this in a probably pretty similar way in one of the previous lectures, and my apologies for the redundancy here. But anyway, this is the graph Laplacian for the star graph. Notice that the one row and column is connected to everything, but otherwise it's kind of just minding their own business, right? There's no connection between like 2 and 3 or 2 and 4 or 2 and n or anything else except through the 1. Says Neo. But and anyway, so if they all have weight 1, you can calculate the trace of this thing. It's n minus 1 plus n minus 1 ones, which is to say n minus 1 plus n minus 1, which is twice n minus 1. But on the other hand, the trace is the sum of the eigenvalues, right? Which is 0 plus n minus 2, plus the thing we don't know, but it's equal to the trace, and voila. That gives us that the nth eigenvalue is n, as claimed. And I just noticed, because I'm always thinking about like, okay, well, this is great, this is wonderful. If all the weights are 1, then life is pretty. And what if the weights aren't all 1? What if the weights are all something else? And so, if all of the weights are constant, it's kind of the same as 1, because of this simple reason. If we take and increase all the weights to alpha across the board, that means that we're just multiplying the graph Laplacian by a scalar alpha, which means that the eigenvalues are just multiplied by alpha as well. So if the original spectrum, so for the star graph with alpha weights, we'd have a new spectrum in red, as I've written it, 0, n minus 2 copies of alpha, and then n alpha for the top eigenvalue in the graph. And again, if you make alpha as big as you like, you can make the nth eigenvalue as big as you like in this case. Now, when the eigenvalues are not, when the weights are not constant, then it's a much harder problem. And I don't think anything particularly pretty can be said without a lot of work. And there are two other results in lecture 2 of Spielmann. He gives the explicit eigenvectors for the ring graph, this and that, these are the eigenvalues, which of course start at 0. Put k equal to 0 here, you get 2 times 1 minus 1, which is 0. And then, let's see here, the biggest this can be is what? Cosine is at most 1 and most negative minus 1, since we're subtracting it. When this hits minus 1, then we've got 1 plus 1, which is 2. 2 times 2 is 4. So like the ring graph could have eigenvalue up to 4 according to this result. And likewise, the path graph has these eigenvectors and same eigenvalues. So the path graph eigenvalues will range also from 0 up to 4 according to these lemmas. And but that's assuming, again, that the weights of the graphs are 1. If we increased the weights or made them inhomogeneous or non-constant, different weights at different steps in the journey, well then all bets are off. We have to actually calculate. So I'm hoping this is laying a foundation for more, giving you a better sense of like what we know about how the formula for the graph Laplacian works. I probably should come back and address the homework problems next. So I'll stop here for now. I think next up I need to go back and look at the normalized versus the unnormalized graph Laplacian. But the other future direction, of course, would be looking at further lectures in Spielmann. I probably will not be as in-depth as I have been here, but we are interested in at least understanding the results that are stated in Fiedler's papers and some of the more recent reviews. So I'll stop here for now. Thanks.